When a major software project collapses, the culprit is rarely a physical hardware failure or a typo in the codebase. Statistically, over half of all IT project failures trace back to a completely different source: deeply flawed initial requirements. The code can execute perfectly, yet the system as a whole still falls apart. Consider a logistics company building a new inventory system for its warehouse. During the planning phase, the corporate security team issues a strict mandate. Every worker's handheld device must require a 16-character alphanumeric password, updated every 30 days with no repeated characters. On launch day, the system grinds operations to a halt. The warehouse workers are wearing thick protective industrial gloves. They physically cannot type complex, randomly generated strings of characters on tiny touchscreens. To keep the warehouse moving, workers start writing their secure passwords on sticky notes and slapping them directly onto the back of the devices. This split-screen comparison illustrates exactly how a failure like this happens. On the left side, we have verification. Verification asks an internal, process-oriented question. Did we build the system right? Did the software match the blueprint? Did it pass the security audit? For the warehouse system, the answer was yes. It scored a perfect 100% on verification. But on the right side, we have validation. Validation asks an external, reality-oriented question. Are we building the right system? Does it fulfill the actual needs of the people using it in their physical environment? The warehouse system entirely failed this test. Achieving a perfect score on verification is meaningless if the final product fails validation. Flawless syntax and bug-free code offer absolutely no protection against building something completely useless. Validation typically fails because systems engineers treat project requirements as objective math problems. They take requests at face value, completely ignoring the messy, conflicting human needs that generate those requests in the first place. Social scientist Christopher Moore categorized these underlying frictions into specific conflict types. What looks on paper like a simple data conflict, an argument over how fast a login screen should load, is almost always masking a deeper interest or value conflict between different departments trying to protect their own metrics. Take a global e-commerce platform. The European legal team demands a strict, multi-step consent process to comply with privacy laws. Meanwhile, the North American marketing team demands a frictionless, one-click checkout process to maximize sales. Both sides refuse to yield. This flowchart demonstrates why the standard instinct to negotiate a compromise is fatal. If the development team tries to build a middle ground solution, say a 2-click checkout with a small legal disclaimer, it fails both objectives. The company gets sued in Europe for violating privacy laws, and they lose thousands of impulse buyers in America. The structural solution is a technique called definition of variance. Instead of merging the demands, the system routes them. The architecture is built to read the user's location and separate the experience into 2 parallel paths: a strict legal flow for Europe and a rapid checkout flow for North America. Building 2 entirely different checkout experiences increases the system's complexity and requires a larger development budget. But when core organizational values are in direct opposition, separating the architecture is the only viable path forward. Resolving requirement conflicts is rarely about forcing stakeholders to meet in the middle. It requires engineering an architecture capable of absorbing irreconcilable human differences. Even when you think those conflicts are resolved, there is a second major pitfall: the dangerous assumption that a formal written sign-off equals actual agreement. Imagine an enterprise software project where the engineering team sends out a dense 100-page technical specification document to a dozen department heads. Exactly 1 week later, every single stakeholder replies with a unanimous, "Looks good." That rapid consensus is a massive red flag. It is a symptom of indifference. Busy logistics managers and finance directors do not have the time or the specific technical expertise to read hundreds of pages of text and accurately translate those words into real-world impacts on their daily workflows. They approve the document simply to get it off their desks. This diagram highlights the limitation of static validation, which relies on reading text, versus the necessity of dynamic validation. A block of text rarely connects with how a user actually operates, but an interactive model forces immediate engagement. Dynamic validation involves putting clickable mockups or rough visual walkthroughs into the hands of the users before a single line of back-end code is written. When you force a user to navigate a flawed simulation of their daily job, their critical instincts take over. The friction of the mockup drags the harsh, necessary feedback out of them, while the project is still in the planning phase and safe to alter. True validation has to be actively experienced. The human brain is notoriously bad at judging abstract technical specifications, but it is excellent at pointing out when a tool feels wrong in its hands. This project timeline visualizes a strategy known as shift left. By combining active conflict resolution with dynamic prototypes, the goal is to drag all the arguments, errors, and design changes as far left on the project schedule as possible. The math behind this is unforgiving. Changing a feature during the initial mock-up phase costs pennies in labor. Discovering that same flaw after the system is fully coded, deployed, and halty warehouse operations costs millions. This entirely redefines the role of a requirements engineer. The job is not to act as a passive stenographer, simply writing down whatever features a client asks for. The true job is frontline diplomacy. It requires navigating complex organizational politics, extracting hidden motives, and having the courage to philosophically question if a requested feature should even exist in the first place. Passing an audit is only half the battle. To build something that actually survives contact with the real world, engineers must verify their code against the rules, but they must relentlessly validate the system against the messy, unpredictable reality of human behavior.